Hello everybody. In the last video, we discussed about recurrent neural network and its mechanism to handle the forward propagation in each time step, along with some code examples. In this video, we are going to learn about the training process of a recurrent neural network, specifically the problems involved in recurrent neural network training, and thereby we want to learn one of the major problem involved here, which is exploding or vanishing gradients, which prevents RNN to learn large sequence dependencies. So this is where we left in our last presentation, talking about the many to one and one to many sequence. So for training, we want to start from many to one. Given a long sequence, we have finally one output, which is YT. And because it is one output, there is no need for indicating the time step, therefore it is equivalent to Y. For training, we have a label available with us, and between this label and the prediction, there is a difference. That difference is calculated as the loss. Typically, a cross entropy loss is used as the loss function, which you can see is a negative log likelihood of each of the element, where Y hat is this prediction value and Y is the label. I is for n number of classes, which are nothing but these elements, then summed over is the total loss for this. When we go to the many to many network, then since we have multiple output at each time step, we also have labels corresponding to each time step. Therefore, obviously the loss also has to be calculated for each time step. So earlier we had only one loss L for the final output. Now for each step we have L1, L2 to LT losses, and you can see that the prediction and the labels values also have changed to their corresponding value. So this is how the loss calculation differ from a many to many and many to one. We are coming to the core topic, which is backpropagation in time, or in short it is called BPTT. The losses, although are calculated in each step, finally they are summed up or they are aggregated by calculating their average. Once that is done, the second thing we want to notice here is that the weight which we used in our coding, during that time also you have noticed that they are actually shared weight amongst the time step, which means, for example, if we are taking this feed forward weight at time step 1, 2 and up to T, they are the same weight matrix which are used and shared across the time steps. Similarly, the bias and this. So these are the shared parameter. Our training objective, as you know, is minimizing the loss with respect to these parameters. So if the loss function is represented by this inverted bowl, where we want to go is the bottom part of this bottom center of this inverted bowl, where the loss is minimum or it is the minima, and we want to understand the slope of this bowl so that we can travel along this path to reach to this minimum. And when we want to calculate the slope, it is nothing but a differentiation or the derivative of the loss with respect to the parameter. The first parameter we are taking is this WD, the weight for the dense layer. Okay. However, we don't have access to this weight at this moment, because what we have here is the prediction from the model, which is YT. Therefore, we are taking help of chain rule of differentiation. Standard backpropagation, I am just reiterating so that we can go to the very specific to BPTT part. So before we go there, we continue with the conventional backpropagation, which is taking help of the intermediate variable to calculate the loss. This YT, which is the prediction, can be replaced as WX plus B or WH plus B from our previous video. We know that. So therefore, this can be differentiated with respect to WD, and then the WD differentiated with respect to tau D will result in HT. We got that HT here. Now it has to be multiplied by the term which is dou L by dou YT. You can see these are the two values which we have during the loss calculation, right? So this is what we have, and we also have the HT which is calculated during the feed forward time. We just have to multiply. However, the dimension is not matching us to enable the multiplication. So we transpose this so that the multiplication can happen. You can see that it is a transpose of the HT, the hidden output. Also, it is summed up across all time steps. Time has come to update the weight, which is nothing but adding or subtracting the weight with the calculated gradient. After that, you go and replace the weight which is there in that layer. This process will continue for all parameters. For example, WF, WR, B and WR1, the layer 1, like that it will go, and horizontally backpropagate it is the standard rule of backpropagation. When you want to go to the next layer, then we are interested in this W, but before going there we have to do the differentiation of loss with respect to HT also. So we want to calculate that first. Let's go there. Differentiation of loss with respect to the hidden output at the very first time. What we mean by first time is the last step, because we are going reverse. While in the feed forward, HL was the, or H1 was the first time step. During backpropagation, HT is the first time step. And there is nothing before that. So there is no dependency on HT. We are saying that now the loss is dependent only on HT because there is nothing prior. This again can be broken into this two term, loss with respect to what we know, YT, what we have here also. You can see what we have here also. We are getting into this term, and another term which is loss of YT with respect to HT. This will be again expanded with the formula of neuron, and then HT of dou HT will result 1, therefore we will get only WT. To facilitate multiplication, we will again do the transpose, okay, to adjust the dimension, and then a multiplication will be available. Now see what is important for all of us to note. Here is the pattern which we are noticing, which can be repetitively applied to calculate the loss with respect to a hidden state. Which means to calculate the loss with respect to a hidden state, we calculate the loss with respect to the predicted value of that time step, which is this part, and then multiply it with the connecting weight. Okay, what is connecting weight? We are trying to calculate loss of YT with respect to loss with respect to the hidden state, and that is giving us the weight. The hidden state vanishes and we just get the weight. That's a very important pattern, mathematical pattern, which we can repetitively apply. Okay, now let's go to the next time step, which is t minus 1. For this example, there could be many steps in between, but let's consider our t minus 1 is H2, yt minus 1 is y2 therefore. Okay, fine. Now when we are coming to this stage, we have two things to consider. One is the horizontal backpropagation, just like the one which we have done before, but added to that is the dependency between HT and H2 or HT minus 1. It is dependent on. That's why this term is also added here. Okay. It is again expanded in the similar manner that when we want to calculate the loss with respect to the hidden state, we calculate the loss with respect to the predicted value, which is y2 here, and also we want to calculate this, which will result into weight. However, when you come here, this weight is not WF, but this weight will be the WR. notice here in the following step. So we are saying that differentiation of loss with respect to y2 is what we have. For the remaining term, we just multiply that with the connecting weight, which is WD between these two relation. And for the time axis, we can see that HT relationship with HT minus 1, HT with H2 is connected via WR, recurrent weight. So following the same pattern, we multiply that by WR. As we progress to the last step for backpropagation or first step for the feed-forward propagation, we are getting into some interesting pattern where all the H have vanished. The hidden state, because of this derivation, you can see HT tau HT will result into only weight. So that's what exactly has happened. For all the time step when we have done this derivation, our hidden step at the time axis have all vanished. And also because of t number of time step, and the first time step has no dependency, we have got t minus 1 power. So it will be multiplied that many times. And this one is the very important mathematical formulation which is indicating the reason for the RNA not being able to handle long sequences. Because this, when multiplied by the gradient either vanishes or it explodes. And why it is so? Let's understand that. Are these values which is there in the weight are tiny, and that is why it is when it is raising to the power it becomes more tiny, and that's how the reason. Very similar to that, but it is not exactly the element of the matrices, but it is the eigenvalue. And to understand the, or rather to remember the eigenvalue, let's go back to the linear algebra and think about it. So in linear algebra, we know that a matrix, which is weight matrix in this case, A, we denote it as the A, just to correlate to the linear algebra, and the vector, which is V here, is the gradient. So we consider the gradient as the vector. In these recurrent neural network cases, that vector will be a high dimensional vector possibly. So there is a vector on which this matrix is applied, which is nothing but a linear transformation. And in the linear transformation, what we get is that the vector gets rotated, changes its direction, and gets scaled, either gets stretched or squeezed. In some special cases, when the direction is not changed but the scaling happens in the same along the direction, okay, that's the time when you say that this vector is a eigenvector of the matrix, right? And then we can have this formula here that a matrix multiplication on the vector for those cases where the vector is only stretched is nothing but multiplying the vector by a scalar number or a set of scalar number which is diagonal. So that's how it gets scaled, which is lambda. Fair enough. So basically multiplying the matrix becomes with the vector becomes easier, and it gets stretched or squeezed, either scaled up or scaled down. Now, do we really calculate the power of a matrix? No, fortunately no. That's a very difficult task to do, very costly for computation. What can be done by this linear algebra formula is that raising a power to the matrix is and multiplying to a vector is equivalent to raising a power of the lambda itself, which is the eigenvalue, and then multiply it, which is much simpler because either it's a scalar number or it's a set of scalar number across the diagonal line, and all other values are 0. Therefore, that raising the power is very simple. So this formula serves two purposes. One, to calculate the power of the matrix, and second, multiply this value with the eigenvalue with the vector, thereby only stretching the vector. What happens is that the eigenvalue, once we calculate, this can be either positive, I mean this can be either less than 1 or it can be greater than 1. Before we come here, a short explanation how we have arrived from the power, raising the power of, or how we prove this formula is just by applying the associative law of multiplication, matrix multiplication, which is you can the A square can be written like this, and then AV can be replaced by lambda V, and then again we do this since lambda is a scalar, then it can be taken out of this associative law. It can be moved out of this product. Again replace this by AV by lambda B, and then these two lambda square up, giving you this final formula. This formula holds for any value of k. So now we said that when this lambda or the eigenvalues are less than 1, then the impact of the multiplication actually there is no gradient at all. The gradient vanishes. Therefore, if we go here in this step, okay, if we are here, you can see that the update of the weight with the gradient doesn't happen. So the weight never gets updated. Okay, so that's the vanishing gradient problem. When it explodes, then it suddenly converges. Training cannot progress anymore. These are the two problems which can happen, and this is how the mathematics explain the reason for vanishing and exploding gradient, which in turn affects the ability to handle long sequences by RNN. It cannot learn long sequences. Okay, so that's about the vanishing and exploding gradient. We want to also go and learn some of the techniques which will be useful later, even for the advanced model. Let's go there. So apart from the gradient vanishing and exploding problem, we have also noticed the dependency between the hidden state. This is the only source of feedback, and this is the only source why RNN is recurrent in nature. As a result, when you are trying to calculate the gradient of H2, let's say, we are dependent on HT, which means that the previous step also need to be calculated, and the vice versa. Therefore, during the feed forward time, the training need to wait till all these hidden states are calculated. Even though the training time, we have all the words available with us and the levels available with us. So the question was, could we solve this problem somehow? See, if we would have removed this connections, the feedback from the hidden state, all the prediction could have been done parallelly. Given all the words, it will do some prediction. Of course, the prediction will not be good because it hasn't learned the time steps. The other variant which you can think of is, since the y's are available now, parallelly calculated, parallelly they can also be fed like the previous output of the model can be taken as the input of the current step. So for y2, y1, which is the model's own output at the previous step, has been given. And that's how the AutoRegressive term comes into picture, where model takes its own previous output as the input. That's how the auto comes into picture. So it's the AutoRegressive model between two prediction value. Probability, conditional probability of y2 given the previous output, and summation of the previous step goes on just like that. However, this improves the training time obviously because of the parallelization, but compromises in terms of its ability to learn the input time sequences. So we could again go back, take this idea from here, the auto-regression idea, and combine with the input sequences as well, compromising the training step back to where we were. So we have gone there. Now the model looks like it is conditional probability not only on the previous output of the model, but also the inputs, and the time steps are learned. Goes on till the last time step. We have a autoregressive model like building up to the first time step. All the sequences are learned in this. Taking these ideas further, we can understand there is a problem during the training time if you are considering model's own input, model's own output as the input to the next step. What happens if the model have predicted wrong? Then this wrong result have gone there as the input to the next step. It has got some. It has got the inputs of the x2, x1 as well. However, because of this predicted output being wrong, it will influence wrongly the prediction of the next time step as well. And like that, the error will keep on building. But we already had the training data, the label data available. Therefore, the auto regression is changed a little bit way. Instead of using the model's own output from the previous step, why don't we use the label as the previous output? And this is what is called the teacher's forcing during the training, where instead of using the model's own output from the previous step, we are using the label from the previous step, and therefore there will be no mistake. Well, this is all about the problems in recurrent neural network training. Especially we have focused and got into the exact mathematical reason why the vanishing and exploding gradient happens for a long sequence, because the power increases t-1 as the sequence reaches to t for the weight matrix, and that gets amplified as the sequence increases. Number one reason. Number two reason is the recurrence. Because each time step is dependent on the previous time step, our gradient calculation is dependent. Therefore, even during the training time, I have all the words available with me and the labels available with me. I am not able to parallelize the operation. We are waiting for the time state to compute. This could be overcome. However, we found that the model will lose capability. However, extending the idea, we could actually incorporate both, combine both of them, and then improve this model's ability to predict much more accurately. And that's what is the auto-regression, which we will be using going forward. There will be a lot of use cases. In fact, the latest of it, which is the GPT model, will be working on this basis. Finally, we said that there is further improvement during the training time, what we are doing by teacher enforcing, not using the model's own output, but using the label to teach the current time step what was the previous output and how it should predict. That's it. And then in the next video, we are going to see how when the sequences are not equal. So far, whatever we have spoken is the many to many, but there is a one-to-one correspondence between these two. When it is not so, then what happens? How do we build that? Is an interesting area, is kind of a point from where we'll be progressing faster towards the current technology. See you in the next video then.